look at that. Okay, so I'm from Mimesis, and just for those of you who don't know us, we work on, I would say, various aspects of medical simulation, from training to planning and to guidance in the operating room. I'm not going to describe what we do in detail, except that I will present 3 plugins we've developed that sort of play a role in those different areas. Starting with a plugin we developed, or actually Alban, who unfortunately could not come today, developed during his master's thesis on position-based dynamics. Okay, so it's available here. It is for now running on a CPU, but we will develop a GPU version starting February next year with a student from Cordoba University. But as I wrote down here, maybe Federico would also be interested in contributing to this. So I have a short thing about that. So well, I guess most of you know, so position-based dynamics, the main idea is to describe the physics of an object through constraints, okay? And it started with super simple constraints, which are basically the length between 2 particles has to stay constant, so you could model hair, basically. And it evolved over time with more and more advanced types of constraints to the point where you can actually do elastic deformations using this approach. Reason we wanted to investigate this is because it's an approach where intrinsically you model everything as a set of constraints. If you solve a constraint problem where you want to put constraints on your model, then this becomes a natural implementation in a position-based dynamics framework. So it can be written as simply as this. It's a bunch of points in space with constraints between them. And the algorithm is also relatively simple. And the main thing here, again, is we process the particles in, I would say, in an iterative way by enforcing progressively a set of constraints between them. And depending on how you enforce the constraints, it pretty much looks like some of the things we do in SOFA, where we use a Gauss-Seidel algorithm and implicit time integration. So I'm going to go very quickly through all of this. But baseline is, once you have a framework like this, the key thing becomes, because this algorithm, as you've seen, is very simple, it's to actually implement a set of constraints that can cover the type of problems we would like to deal with. And so what Alban did is he implemented constraints that work for 1-dimensional, 2-dimensional, and 3-dimensional objects. I will show you some examples if I can run that in my machine, but basically you can model rods, and they can be elastic or non-elastic. You can model surfaces and volumetric objects. So there's a support for the same topologies we have in SOFA. And in terms of constraints, they are listed here. So in 1D, we have a Costrat model and also some springs, so they can be elastic or not. And you can basically add those constraints together and get some new behavior. We have, in terms of elasticity, a nonlinear material, a Saint-Venant-Kirchhoff. We have an isotropic version of it. We have isometric bending. And we have also another type of bending. And we have a similar thing in 3D. So the link to the plugin I showed you before, and I will try if I can some on Mac. Look at that, it works. So again, nothing, we don't have an amazing demo. And again, this is an implementation on the CPU, but you can actually run it in a multi-threaded environment, like if you have OpenMP, for instance. But on a single core, if, for instance, I show you this example, or actually, no, this is just, yeah, so. Well, you see. I know, it's not, but the liver, if I can find it somewhere, the liver model that we have, so if we take the same number of tetrahedral elements, and we get the same accuracy as the FEM implementation, runs about 4 times faster. And that's just using one single core on the CPU. So the idea is to, again, early next year, move that to a multi-core CPU and then on the GPU, because I think with that, we could have some very nice but accurate simulation. There's a little trick in those methods, which is that in that iterative solver, the number of iterations that you set will highly influence the stiffness of the material. That's the main limitation of this method. So if you don't put enough iterations, it will tend to be softer than you want. If you put too many iterations, it will be stiffer. So what we're doing, what we'll do again early next year, is to estimate the value of these iterations to mimic a given type of material using something like, here, wait for the transition, Bayesian filter. Okay, so that's the other plugin we've developed. It was mentioned last year, but the main thing is we are almost ready to release it. The idea of a Bayesian filter or Kalman filter is to, at least in our context, is to estimate properties, parameters of a model. So let's say you want to estimate the stiffness of an object and you only have observations of it in a video, for instance. How can you do that? So there are many methods in terms of the optimization that could achieve similar results, but at least this is a nice framework to be able to work with. And the basic concept is every parameter we want to estimate is assumed to follow a Gaussian distribution. If we know this distribution, meaning you have a mean value and a standard deviation for your parameter, then you have a Gaussian shape. It could be in many dimensions depending on the type of parameter. And then this distribution is transformed over time, in particular when your problem is a nonlinear problem. And it can get ugly, meaning it's no longer a Gaussian distribution. That's the problem with basically nonlinear Kalman filters. So what we have implemented are versions that handle well those nonlinear processes. And they basically work so by discretizing. These are the red points you see here, and the Gaussian distribution has a set of sigma points that allow you to approximate the Gaussian distribution. Then those points are transformed through any kind of a nonlinear process. And then we enter an algorithm which looks like this. The key thing being that for every parameter we have in the model, we initialize the algorithm with an estimation of the mean and the Gaussian distribution. The algorithm will sample this Gaussian distribution by those sigma points, and for every of those sigma points, it will run a simulation and then predict a result. And then later in this algorithm, the result of all those simulations for those values of the sigma points are averaged and combined with observations of the real object. Okay, so with that, you can, for instance, estimate the stiffness of an object if you can measure the position of some points of that object over time. I will show you an example. Before I show you the example, this is again the link to the plugin. I think we'll make the slides available anyway. When I said it's nearly ready to go, because we have documentation, we keep using it, and we just want to open it to you guys. If it's useful, also maybe you can contribute to that. So here's an example where we have a cylinder made of 3 different regions of different stiffness. We don't know what's the stiffness. So we initialize all the values to, well, like 6,000 Pascal in this case. That's our initial guess. And then we have, but it's not easy to see them, some points here on the surface that are our observations. They're measurement points, okay? For now, here they are in 3D, okay? And so those points, they have a different position in the simulation, the prediction, than in the real world. And through the difference between those two, the algorithm will modify the stiffness parameters, but maintaining this within the Gaussian distribution. Bottom line is, as time goes by, but it takes only a few seconds in general, it will converge to a constant value, which is close normally to the true parameter value. But not necessarily. I mean, if your model is wrong, it will find a value which is a good value for the model, but not necessarily fitting the true value of your stiffness of the real object. But it's useful, we think, to, for instance, tune model parameters to mimic real-world objects. So I don't have pictures of that. We, for instance, took a catheter that we simply placed against a vertical surface and measured its shape over time. And if you have a few observations of that, you can estimate the Young's modulus of the catheter and feed that into the model for some other simulation. We also used it to estimate a more complex problem, which is not the intrinsic parameters of an object like the stiffness, but the boundary conditions in our, I would say, line of work. When we want to model correctly the deformation of an organ like the liver, we barely know how it's connected to the surrounding anatomy, because it's not some information that's visible in the preoperative images. So the way we handle that is by saying, okay, well, somewhere, but I'm not sure where, around my organ, there are some connections to the anatomy. So we create lots of springs. In our case, they are nonlinear springs that describe the possibility that here there's a connection to some other structure. And the algorithm, by looking at those videos, will estimate the stiffness of the springs. And if there is no boundary condition, it will set a very low stiffness, meaning that there's no actual, so it's free of motion. And that actually also works well. And when we do that, for instance, we can get simulations that are much more accurate than if we don't account for those unknown boundary conditions. Last plugin. We're a bit behind. I was hoping to show you a demo today, but I have a Mac which doesn't have an NVIDIA card, and it's complicated when you want to do machine learning. But I want to show you some results on what we've done to basically model, simulate in real time the deformation of complex structures using machine learning. So it links to what Eleonora was showing earlier, except I will replace the breast by livers. So what we've done basically is we have developed a method where a plugin where we can train a neural network. In our case, it's a particular network which is a UNet to learn the relationship between some input to an object, which could be either a force or a constraint, a displacement, and its output, which is a displacement field. And we do that by training the network with simulations. And to keep the training time limited, we actually sample these inputs in a way that we sort of optimize the training data set. A network looks like this, and the reason we chose this is because it mimics what happens when you do model order reduction. When you go down this path here, which is called the encoding path, you reduce the dimensionality of the prime to a vector of a few hundred scalars that basically describe the deformation of the subject under this particular input. And the encoding path, which is going up, basically upsamples this to the initial number of degrees of freedom. So in a more visual way, it looks like this. We generate lots of deformations on an object, could be anything, and then we train the network with that. Altogether, this takes less than a day, okay? Meaning generating the simulations and the training. And then we can play with that, and you can see, at least visually here for now, but we have some numbers as well, that it pretty much gives the same result as the FEM computation, but there's a big gain in terms of computation time, and the gain goes up as you increase the complexity of the model, because the neural network predicts always in a very short amount of time. So we've applied this to different types of structures, and for now, at least, we've got good results, and it's relatively, but with quotes, insensitive to variations in terms, for instance, of stiffness, or even what it was trained with. And I've made some recent mistakes when I was testing things and not applying constraints, for instance, where the network had learned that, and it still predicts something which is reasonable. And if we change slightly, for instance, the stiffness of the object on which it was trained, it still gives a pretty good accuracy. If we change it a lot, of course, or we change significantly the boundary conditions, of course, makes a big difference. And here you can see, again, visually and more in terms of numbers, how those different things compare. So we are even faster than the co-rotational model, but with the accuracy of Savin-Kirchhoff. And again, it's because we trained using that model. I think we could probably go beyond that. So we've applied it to some augmented reality scenario where, in the end, instead of just comparing to a numerical simulation of the same lever done with FEM, we actually have a real lever that we scanned in 3D under different constraints, and basically what we get is a prediction below 3 millimeters of its actual deformation, but in 3 milliseconds. And here, just some, what I cannot show you, examples of like where we are at right now. So we're at a point where we can have in SOFA an interaction between a FEM object, like that's my little sphere, with a machine learning simulation for the beams. So it's possible to have some sort of multi-physics interaction, if you want, between objects which are on some end simulated the classical way, and the other end computed using a deep network. And the next step, because all of this is done as a static simulation, next step is to, which we are working on right now, is to do dynamics. So see if we can not just predict the deformation of an object, but predict its dynamical behavior, and so take time in a way into account. On that, I will stop, and thank you again.
Yeah, Noah has a very important question.
Okay, so I'm interested about this idea of using simulations to generate data to train the network, right? So you generate some deformable levers or beams or whatever. Do you apply like some constraints on this deformation, like about the volume? Because sometimes, I mean, can you accept any deformed shape as your training data? Yes, I mean, should we like define rules for the deformations when we generate this data, or it is fine like?
Well, the only rule we have is if you want to minimize the number of simulations you have to generate and the training time, there are some rules that we apply to, I would say, optimize the training. Because normally when you train with real world data, you don't choose your data. So the basic concept is take as much data as you can. It will find a way to do some magic here. Generating a million samples would take a long time, and we want to minimize this. So we have some rules, but they're not really complicated to, I would say, optimize the training set. But then in terms of the model that you can train with, no. Even in terms of geometry, because at some point we were limited with basically everything that would be more or less like a sparse grid and using hexahedral elements, but now we can train if we have tetrahedral meshes and any shape.
Okay, maybe that's because, for example, in real life we cannot imagine a liver which is deformed in such a way that, you know, it is very deformed. There are some limits for these deformations. So should these rules also, I mean, be applied on the training data?
It's a good idea to do this, yes. But I would say if you train with very large deformations, but in your real world scenario, you don't see those things, it's better this way than the other way. Those networks, in general, that do regressions, they are very bad at extrapolating. So best idea is to cover the largest possible spectrum of deformations in your training data set, even if you never really use this case.
Okay, you have two other questions in the back here.
Very nice work. Do you think it will be possible one day to, instead of train your network with a parameter, to train it with topological chain? So for example, remove some elements.
Somehow I knew this question was coming. I don't know, really. I would say it must be possible. I'm not sure I have an idea how to do that. It should be possible. We are, for now, because we use this UNet architecture, we are a little bit constrained in terms of topology, actually. So that's why I'm saying I'm not sure. Maybe with some other architecture it could be, but I don't know. It'd be nice, huh?
So, and we are talking a lot about machine learning, but the two other plugins actually, you know, the Optimus for using Kalman filtering, helping, you know, definition of patient-specific, for instance, parameters, and the position-based dynamics are also, I think, two interesting plugins to actually use for any of your.
Actually, PBD for topological change is your friend.
So just one quick question. I don't know if you here, what you're doing is you compute a displacement under a certain force. But do you also compute the stiffness? In other words, can you make have some haptic feedback using this neural network? Or?
That's what we did before this work, where we were actually computing haptic feedback for a robot. So not haptic feedback, but basically force feedback for a robot based on images. So we trained the network to understand the relationship to the other way around, from an input which was a deformed configuration, actually an image in that case. We learned what was the force, the reaction force, or the force that you needed to apply to do this. So I would say on that basis, what you propose should work, yes. No problem.